Hey everyone, in this video we're going to talk about journal bearings and specifically looking at Sommerfeld number, stable lubrication, and solving an example problem. And this video is part of a lecture series on mechanical design too. So we're going to get started by just introducing the Sommerfeld number. In the previous video in part 1 of module 4, we talked about Petrov's equation and we came up with an equation for Petrov equation that was derived theoretically for bearings. And in this video here, we're going to be expanding a little bit further on that and introducing how we can use charts in order to solve our problems. And the best way to introduce charts is to actually look at some tables that were developed based on a similar application to Petrov's equation, but using experimental data to build them. These charts are going to be available throughout these video lectures. So we'll be looking at the chart for every video pretty much from now on, and those are Raimondi-Boyd charts. And we're going to start with what the Sommerfeld number is and where it comes from. So we remember that in the last video we had Petrov's equation, and we had written Petrov's equations with two different dimensionless numbers, which defined essentially Petrov's equation because the other term was 2 pi squared. And those two terms, the nice thing was that they were dimensionless, and they basically determine the performance of your bearing or the amount of friction that comes out of your bearing. So another person came along and made up a new way of looking at these two terms and created a Sommerfeld number. And the Sommerfeld number was then used to essentially non-dimensionalize graphs for different types of bearings and different sizes of bearings, and they were all normalized, so you can use them for all bearings essentially. And the Sommerfeld number just combines these two terms. Instead of having 2 pi squared times mu n over p times r over c, what the Sommerfeld number is r over c squared times mu n over p. And then based on that, what Sommerfeld can do is, so R over C is first of all called the radial clearance ratio. But what Sommerfeld did is he then said, well, based on this number, we can then go to our charts, and I'll go to module 4 formula sheet, and we can see that if we go to, for example, a chart for friction, okay, you can find your bearing characteristic number, okay, which is also called the Sommerfeld number. S is equal to R over C squared mu n over P on the x-axis. And we see that we can relate that to a coefficient of friction variable, which is also dimensionless. So we have a dimensionless term here, because everything is dimensionless within here, compared to another dimensionless term here, and we have a graph that is basically applicable to any journal bearing. So then, based on the S value, we can find very, very quickly what our coefficient of friction would be. Okay, so we're going to see how we can use that within the context of example problems. So we're not going to learn it like step by step, each graph means this graph means this, but it's much easier to learn through an example problem. So that's what we're going to be doing in this video. So that's the first thing, and we'll come back to that in a second. But the other thing that we want to learn about is learning about stable lubrication. So we talked a little bit about how we want to have thick film lubrication whenever we have a system that is in hydrodynamic lubrication. So thick film lubrication is synonymous with stable lubrication. And stability is very important, meaning that we're going to have a lubrication that is predictable. Okay, this is also sometimes called thick film lubrication. And this is also essentially a way of telling us, since the assumption for Petrov's equation is that we do have stable lubrication or we do have thick film lubrication, Petrov's equation is only valid for certain parts of our analysis. And really, we only care about thick film lubrication, because if we have thin film lubrication, that means we have unstable lubrication, and we don't really want that. So now what we want to look at is to try and explain this concept of stable lubrication. What we can do is we can draw a graph of friction versus mu n over p. Okay, so we're going to write and I'll bring this problem down that we're going to be doing in a second, so I'll just bring it down so we have a little bit more space. But we're going to draw a graph of F versus mu n over p. So mu n and p. So let's think about those for a second. Mu is viscosity. We can control viscosity within a problem or a given design because we can choose the fluid that we're going to use. We can also control the velocity of rotation of our bearing. Obviously, based on our application, we might not be able to control it, but hopefully we'll be able to control it to some extent. And then pressure we can also control by changing the type of system that we have. So the three different terms altogether can be controlled. So this term is a term that we can control. Friction, on the other hand, is a resultant of these three things, okay? Now, we also know that we can control geometry. We can control R over C as well, and R and C if we want to. But in this case, let's just take into account that R and C are going to be constant, and the only thing we can control is mu n over p. And if we draw a graph of friction versus mu n over p, as mu n over p increases, so mu n over p increases, what we see is the following. We see that friction is, so let's start at somewhere here where we have an actual value for mu n over c. And what I'll do is I'll draw a dotted line all the way up, okay? If we look at our mu n over c, what happens is it looks something like this, okay? It's pretty much a straight line. It's not exactly a straight line, but it's very close to being a straight line, okay? And this part is predictable, okay? If we increase mu, we're going to increase friction. If we increase n, we're going to increase friction. If we decrease p, we're going to increase friction, okay? It kind of makes sense. Okay, now the important thing that's what's happening is before this point that I drew, which we'll call point C, and we'll call this point B here, okay, we'll call this line AB essentially, so between line AB. Before line AB, what happens to our friction is the following. We have this crazy increase in friction when we go too low in the mu n over p. And what this means is essentially in this part, we have what is called unstable friction. And in this part to the right, we have stable friction. Okay, in other words, here we have thin film lubrication, meaning that our viscosity multiplied by n over p is too low. So usually our viscosity is too low and we end up having metal-to-metal contact and it's very unpredictable friction. If you change your mu n over p very slightly, it's going to increase your friction a lot. So what we try and do is we try and run our system anywhere from this point to the right. Okay, so that we have a predictable friction increase and we know kind of how much friction we're going to get, and we know that if our mu n over p changes slightly, we're not going to get a huge change in friction. It's very predictable, and that's what we want. And so that also means that Petrov's equation is valid only to the right of line AB. Okay, there's no way Petrov's equation could be used for the left side. Whereas if we wanted to use the left side experimentally, we could, we just wouldn't want to do that. We usually don't, we want to try and avoid that. So what we can write as a conclusion of this graph and this conclusion of an experiment that we can run, okay, we can run many of these experiments, okay? What we can conclude is that if we have typically what we see when we have unstable lubrication, which is to the left of line AB, we have what is called thin film lubrication. We have a thin film, and what this thin film creates is metal to metal contact, which increases the friction a lot. Essentially, the fluid is not able to maintain our system in place in the center. What happens is essentially our journal and our bushing, over exaggerated obviously, are going to be touching on the surface, and this bushing is going to be moving in all directions and not really staying centered enough. So we don't have thick film lubrication. So what we've done is what they've done is basically, after a lot of research and a lot of time spent on this and spent on experiments, they determined that Sommerfeld and others determined that to keep thick film lubrication at all times, your mu n over p value for any bearing, because it's a dimensionless number, is going to have to be greater to 1.7 times 10 to the minus 6 times 10 to the minus 6. And since it's a dimensionless unit, we can keep it dimensionless, but we have to make sure that mu n over p is dimensionless. So we have to use the right terms for mu n over p. So the terms, or the units that you would use for mu n over p, would be rain times RPS divided by PSI. But you could use this in SI units as well. As long as the units cancel, then you would be good to go. Okay, in SI units, it's actually easier to cancel the units, so that works pretty well. So this means that we have a clear understanding of, we need to keep thick film lubrication for most cases, okay? Usually we don't have to not get thick film lubrication. And then in order to find our friction, which is the only thing that we know how to find for now, we could either go to find our Sommerfeld number and then use a chart to find our friction, or if we have thick film lubrication and we know 100% we have thick film lubrication, another option would be to use Petrov's equation. But it's usually always preferred to use a charts if you can. But you can use Petrov's equation if you want to as well. So you'll see in your formula sheet for module 4, you'll also see that at the top here, you have some equations, and you'll see that one of the equations is mu n over p is equal to 1.7 times 10 to the minus 6. So we have that term. We have also that P is equal to W over 2RL, which we've talked about already. We have that torque is equal to FWR. We've talked about that already as well. The other terms, these terms we haven't talked about yet, so we'll have to talk about those. And this we haven't talked about, but we'll talk about as we do some example problems. Okay, so what we're going to be doing is we're going to be moving into an example problem to try and solve this example problem and try and understand how we would use all the things that we learned so far to solve a problem. And we're going to learn new things as we go, because the problems are going to ask us to find other things than just the friction for our bearing, because there's other conditions that need to be met, but we'll talk about those other conditions later on. Okay, so let's start and try and solve this problem that's listed below. So we have a full journal bearing has a journal diameter of 25 millimeters. So we already know that we have SI units. Okay, and we're told that we have a journal diameter of 25 millimeters. So what I like to do is I like to just draw a diagram and say, okay, my journal has 25 millimeter diameter, okay? And then it tells us it has a unilateral tolerance of minus 0.03, okay? So we'll talk about what that means in a second. But what it means is unilateral means one-sided. So that means that the machine shop people are essentially told that you can only have a tolerance in one direction. So we have to make sure that our journal diameter does not exceed 25 millimeters. It can be 24.97 millimeters, but it can't be 25.01 millimeters. And the reason why is because if you look at the space between the journal and the bushing, it's a lot smaller than we actually think. Okay, it's not, we always draw them over exaggerated just to make sure that we have the gap, but the bushing itself, which I'm going to draw separate, okay, but you could draw them on top of each other, is going to be 25 0.03 millimeters. Okay, and it has a unilateral tolerance of 0.04. So that means that the journal and the bushing can never essentially be the same size because of that unilateral tolerance. So the bushing could go up to 25.07 and the journal could go down to 24.97. So the gap between the two could increase, but it would never be smaller than 0.03 millimeters. So the gap in between is always going to be 0.03 millimeters. Okay, then we're told the L over D ratio, so L over D ratio is equal to 1/2. Okay, and we're going to need that information in order to solve some of the problems that we have because the graphs are given for different L over D ratios. So L over D just means the length of your bearing versus the diameter of your bearing. So the length is essentially when you have your bearing like this, okay, with a journal and a bushing. So let's say that this is the part where you have your fluid, this is your journal, and your bushing is on the outside. Then your length is this, and then your diameter would be your diameter of your journal, okay? So the L over D is important for our design because we need to keep it to 1/2 or 1 or simple numbers if possible, and there's different results for different L over D ratios because of how bearings behave, essentially. We're then told the load is 1.2 kilonewtons, and the journal runs at 1,100 revs per minute, okay? So we're told that information, so we know that this information is going to be important, and this information is going to be important. And then we're told if the average viscosity is 55 millipascals seconds, find a bunch of different things, okay? And we're going to go through each different things, a bunch of different things for the minimum clearance assembly, okay? So it's going to be for the minimum clearance assembly, okay? Which minimum clearance assembly means that there is the smallest clearance possible between these two systems. And we can clearly see that the smallest gap possible between these two systems, if we take out the tolerances, is going to be the 0.03. But we'll look at that in a second as well, okay? So I'm just going to note down some of the things that we have, okay? And I'm going to write down the notation that we use. So we have L over D is equal to 1/2. We already wrote that down. Then we have W is equal to 1.2 kilonewtons. We have that diameter is equal to 25 millimeters. That's the diameter of the journal. We have N is equal to 1,100 RPM. We're told that B, which we're going to use for the bushing diameter, is equal to 25.03 millimeters. And obviously these values could be different, but again, we're looking at the minimum clearance assembly. Therefore, we're keeping the gap as small as possible between the bushing and the journal, okay, which is what is intended for initially. And then mu is given to us as 55 millipascals seconds, okay? And we're told at first to find, the first thing we're told to find is find the minimum film thickness. So this is where we're going to learn new things, right? So we're going to find the minimum film thickness. So I'll put min film thickness first. Okay. And what the minimum film thickness is a value called H0. And this is when the journal is off center. When the journal is off center, we can find a minimum film thickness, and that minimum film thickness is going to be a thickness that, if we look at our bushing and bearing together, so let's say they're off center, it would be this height, H0, that would be the minimum film thickness that you're looking for. And for now, we're just going to look for them. We're just going to basically go find the value and plug it in. Later on, we're going to understand what that number actually means and what it should actually be, okay, and why it should be a certain value. But it defines the film thickness that you need to maintain in order for there to not be metal to metal contact. If H0, for example, is equal to 0, then you have a big problem. If H0 is equal to 0, that means you have contact between the two metals, and that's bad. If H0 is too small, we could have some issues, which we'll talk about in a later video as well. Okay, but for now, we're just going to look for H0 based on the information that we have. Okay, and what we're going to do is to find H0, we're going to use our tables. And we're going to look at our tables really quickly. And we're going to see that our tables have a bunch of different things. So our tables have charts. So the two first charts are viscosity versus temperature. So we have absolute viscosity versus temperature for SAE oils and for 20W50, 20W40, et cetera, et cetera, et cetera. Oils. Then we have a coefficient of friction variable here. Here at the bottom, we have a position of minimum film thickness, which we're not really going to look at much, but it does give you the position of the minimum film thickness. Here on the left, you'll have the minimum film thickness variable, which is the one we're interested in now for now. And then we have more charts on the second page, which we can look at later on. But we have flow variable, temperature position of film theta, flow ratio, as well as maximum film pressure ratio. Okay, we'll look at all of that. Then the last thing that we have here is a interpolation that we can do if our value of L over D, if L over D is not 1, 1/2, or 1/4, which we see that 1, 1/2, and 1/4 are on all of our graphs. If we don't have other values, then if let's say our L over D is 3/4, then we can do an interpolation based on our values here. So we could just plug in our L over D here, our L over D here, here, here. And then we have Y infinity would be, for example, if our Sommerfeld number is 0.1, then our Y infinity would be this value, our Y1 value would be this, our Y1 half would be this, and our Y1/4 would be this. And we just plug in our Y infinity, Y1, Y1 half, and Y1/4, and we would get a value of Y. Okay? This is not something that would be asked for on an exam, but it could be something that could be asked for in some problems, for example, in a book like Shigley's Mechanical Design. Okay? So let's go back to our problem, specifically looking at minimum film thickness, because that's what we're looking at right now. And we have an L over D of 1/2. So we're going to be using this line of the chart. So I'll highlight the line, but it's going to be this line right here. Okay, we're going to be using this line of the chart. And in order to find H0, we need to find C, okay, because we have H0 over C. And we also need to find our Sommerfeld number. If we can find our Sommerfeld number, we can then go to the chart and basically, let's say our Sommerfeld number is 0.2, we could go up, find this, and then we could go across and find the value of H0 over C. Okay, just an example. So let's erase that and let's get started with trying to find that. So first, finding C and also finding Sommerfeld number. So let's go ahead and solve for the Sommerfeld number based on what we need to find H0. So for now, we're just trying to find these values. Later on, we'll talk about the utility of these values as well. Okay, but H0 is when it's off center. You basically want an H0 that's greater than 0, and hopefully it's big enough based on the criteria that you have. But we'll talk about those criteria later on. Okay, so we're going to go to our charts, and based on our charts, we have to find S. Okay, so we're going to use our charts to solve this problem, and we need to find S. So we're told that S is equal to R over C squared times mu N over P. And that's also given in your formula sheet. So you have it in your formula sheet. It's on the bottom of every graph. Okay, so first things first, we can write R. R is going to be the radius of our journal, which is 12.5 millimeters. Okay, very easy to solve, 12.5 millimeters. Now, let's kind of draw a diagram of our system exaggerated. Okay, I'm going to draw with a really big gap, but this is 25 millimeters. And then this is 25.03 millimeters. So I'm making a very big gap just to make the point. Now, C is the distance from here to here. Now, what a lot of people make a mistake of is they say, well, C is the distance between the two, so that means that C is equal to 0.03 millimeters. This is incorrect, okay? This is not correct. C is equal to half of 0.03. 0.03 would be C plus C. So it would be essentially 2C, okay? So it's very important to always use the equation to find C, and you won't have any problem, okay? So C is essentially the following. It's B minus D, so the bushing diameter minus the diameter of the journal, divided by 2, okay? Because the clearance is on both sides, and we only need to find one clearance. Okay, so our value for this would be actually half of 0.03, so it'd be 0.015 millimeters. Okay, we can see that the clearances are a lot smaller than maybe you had thought about, so definitely keep that in mind when you're doing your problems. Okay, so we have R and C, so we're good to go. So we can write that, I'll put it in green here, we have R, we have C. Do we have mu value? Yes, we have a mu value, so we're good to go. We also have, so we have a mu value, we have, and sorry, I should put it in green, we have an N value, although it's in RPM, we'll be able to modify it to RPS if we need to, and the only other term that we're left to find is our pressure term, so we don't have our pressure term. So let's find our pressure term, and then we should be able to solve for Sommerfeld number. So pressure, based on our equation, so if we go back to our formula sheet, if we go to the top right of the formula sheet, we have that pressure is equal to W over 2RL. Okay, so we're going to write this as W over 2RL. Okay, and this W over 2RL is going to be equal to, we're given W, it's 1200 newtons, divided by 2 times R, which we have, 12.5 millimeters, and then we have to find L. Now, we need to look if we have L in our problem. So we see that we don't really have L in our problem. But we know that L over D ratio is 1/2. That means that L should be half of the diameter. So the length is actually going to be half of 25. Okay, so it's also going to be 12.5 millimeters. Okay, and you can pause the video here if you want to double check or make sure that you're doing the right thing, but that should be able to solve it. So then we can say the pressure is equal to 3.84 newtons per millimeters squared. Okay, I'm keeping the units as is, and then you can convert those units, if you want to Newton per meter squared. So in Newton per meter squared, we would have 3.84 times 10 to the 6 to get rid of the millimeter squared at the bottom, Newton per meter squared, okay, which is also the unit of Pascal. Okay, we don't really need to use the unit of Pascal. I mean, we can write it in Pascal seconds. It would be probably easier, but you can also leave it as is and just work with it in the Sommerfeld equation. So now we have pressure, so we're good to go. So we can start plugging in for our Sommerfeld number. So our Sommerfeld number is R over C squared. So we have 12.5 over 0.015. And I'm going to put here millimeters and millimeters. And since they're both in millimeters, they are going to cancel, which is what we want. Our Sommerfeld number is a unitless number. So as long as we get a unitless equation at the end or a number at the end, we're good to go. If we don't have a unitless number, we need to modify something. Okay, so millimeters over millimeters works. If you had meters over millimeters, it would be a problem. But in this case, we're good to go. Then we have mu times n over p. So mu is given in our problem is given as millipascal seconds. So we're going to convert that to Pascal seconds just so it's easier. So it's 55. Instead of writing millipascal seconds, we're going to write 55 times 10 to the minus 3 Pascal seconds. Okay, everybody should be good with that. Then we're going to multiply that by 1,100 divided by 60 RPS. Okay, we're converting to RPS because we want to get rid of that second terms. Remember, it's revolutions per second. So we want to get rid of the Pascal second term. So we need to divide into seconds and not minutes. All divided by 3.84 times 10 to the 6. And we're going to write it in pascals, since we know that Newton per meter squared is pascals. Okay, and that will allow us to cancel our pascals. So we can close the brackets now, and we can just check that everything essentially cancels in here. So revolutions is not a unit, and then we have Pascal, Pascal, and seconds. Seconds are going to go away. So we're left with a unitless number. And that unitless number is going to be equal to, S is equal to 0.182. Okay, we're also given that L over D, just rewrite it really quick, L over D is equal to 1/2. And now we can go to our chart to find H0 over C. So we're going to go to our chart and find H0 over C. So if we go to the chart with those numbers, we go to the right chart here, and we're given that we have a Sommerfeld number of 0.182. So my Sommerfeld number is going to be around here, 0.182. I'm going to go up this line, stop right here, and then I'm going to go over, and I'm going to find out that my H0 over C is equal to 0.3. Now, be really careful when you're doing these types of problems that you write that H0 over C is equal to 0.3 and not H0 is equal to 0.3. If not, that would be incorrect, okay? You then need to find H0 by multiplying by the clearance. So H0 is going to be equal to 0.3 times the clearance, which is going to be 0.0045 millimeters. So that is going to be your minimum film thickness inside your system. Okay. So the next term we have to find, given in our problem, is we're given that we have to find the power loss. Okay, so again, a new thing. Okay, so we have to find power loss. So power loss is essentially how much power did we lose to friction because of our system. So let's say you put a torque of a certain amount on one thing, how much power are you losing because of friction? Okay, and it's the power loss, we'll write it to friction. So if you're losing power to friction, you can use your torque equation to say that torque is equal to friction times W times R. Okay, we have that torque is equal, and we derived this when we were doing Petrov's equations in the first part of this module. We have that torque is equal to FWR. Okay, and that's a friction term. Okay, if we go back to our formula sheet and we go to the top right of our formula sheet, we'll see that we have that torque at the top right is equal to FWR. So we see, I'll just re-highlight it really quickly, we have this. And then we're also given some equations here for HP loss and H, which we'll talk about later, but that's for US units, not SI units, so we don't have to talk about it now. For SI units, it's pretty simple to solve, so we're going to solve it that way. So for power loss, we know that power and torque are related together, okay, by RPM essentially. So we can say that power loss, which we're going to call H is going to be our power, just like when we study gears. H loss is going to be equal to 2 pi n, okay, which is your rotational speed in radians, times T, okay, where T in this case is the T due to friction. Okay, now based on that, it means that in order to find, so I have my 2 pi n we have already, so we're good to go, but we need to find T. To find T, we need to find F. Okay, and in order to find F, what we would need to do is we would either need to use the Petrov equation and check that we have stable lubrication, or we can just go straight to our charts, okay? So typically, we just say, we don't need to check if we have stable lubrication. We're not told that we have to check. So let's just go directly to our charts, and we don't need to worry about if Petrov's equation is valid, because Petrov's equation is only valid for stable lubrication. So we're going to use tables or the charts, and in those tables, we're going to find F, or we're actually going to find R over C times F. So in the same way as before, we already have our Sommerfeld number, so we can go to our Module 4 formula sheet. We're going to go to the RCF curve this time. We're going to go to a Sommerfeld number of 0.182. So we have Sommerfeld number of 0.182. We have the line that is equal to 1/2, and we're going to end up at this point right here, and we're going to see that we're going to get to something like 5.4. So we see that this is 5, 6, 7, 8, 9, 10. So we see that we're at just under 5.5. If we zoom in, we'll see that we're just under 5.5. It's hard to see, but it's an approximation once again, so you don't have to be exactly precise with your analysis here. There are more advanced tables if you need to, and lookup tables where you can find more exact values. But R over C times F would be equal to 5.4 in this case, based on the chart. And so F could be figured out by doing 5.4 divided by R over C. So we would divide that by 12.5 divided by 0.015, and we would get that F is equal to 0.00648. So we now know our friction factor. So based on our friction factor, we can then find the torque. So we can say torque is equal to the friction factor, 0.00648, multiplied by 1200 units. So that's the 1200 newtons, times 12.5 times 10 to the minus 3. And that would give us a value of 0.0972 Newton meters. Okay, so this is the way to find the torque, essentially, that is lost based on due to friction. Okay, and then based on that torque lost to friction, we can find H loss using the equation for H loss, which is 2 pi times 1,100 over 60. I'm going to keep it in RPS, okay, in order to get the term in Newton meters per second, which is going to be watts, okay, times 0.0972, and we're going to get that this is equal to 11.2 watts. So we're losing 11.2 watts in power loss. Okay, so that solves our second part. Then the next thing we're going to have to find, and essentially all the findings are going to be in the same way, right? So the next thing we have to find is the side flow for the minimum clearance assembly. So we're going to have to find side flow. And what side flow is the following. So whenever you have a bearing, you have a total flow coming in. Okay, so you have a total flow coming in, and you have a bearing that's placed like this, with your journal in the middle, and your fluid will draw in red. Okay, your fluid is here. And whenever you have a bearing like this, you have some seals on the outside. So you try and seal the outside so you don't have flow on the outside too much. However, your flow is going to go all the way around this bearing. Okay, so think of this like as a circular bearing. Okay, so it's going to go all the way around. And part of that flow is going to be flow that's going to stay in, but there's also going to be a side flow. So there's going to be a flow that's going to come out from the side and be recuperated through a sump or through a system. And there's also going to be an exit here for your Q as well. But your Q going down is not going to be the total Q. It's going to be a little bit less because there's going to be some Q to the side as well. Okay, so you're going to have some QS exiting through the side. Okay, but it's all going to be brought back into basically an oil sump, so like an oil reservoir, and then the oil reservoir will have a line back into here. Okay, so that's kind of how it works for side flow and total flow. So there's some flow that's going to go straight through, and that would be, and it's all the flow coming in, and then some flow is going to be escaping to the side depending on your design and depending on how your design works. So there's no real way to seal your system on the outside, so we just let the flow go out, but we know we're going to catch it back in some way. It's a loss, but it's not a complete loss because you can recuperate it and reuse it essentially. Okay. All right, so hopefully that makes sense. But if you want to read more about side flow, your Shigley's book as well as other resources have some information there. So the two terms that we need to know is QS is equal to side flow, and Q is just equal to total flow. And what total flow is essentially the amount of flow coming into our system, and side flow is the amount that's coming out through the sides. The rest is coming out through the bottom or through just gravity, essentially, okay? So what we need to find out is we need to solve for total flow, and then we can solve for side flow. Okay, so first we need to solve for total flow, and we'll see why, and then we can find side flow based on that. So if we go to our problem, we have some charts on the second page, on our formula sheet, sorry. On the second page, we have some charts here. We have flow variable Q over RCNL versus bearing characteristic number here on the left. And we have flow ratio, which is QS over Q. So in order to find QS over Q, we need to find Q first. There's no way to just find QS as a function of just RCNL. So what we need to do is we need to find Q first. Then once we find Q, we can use the flow ratio to find QS. So best way to do this is to just find both terms directly, write them down back on your worksheet, and then you solve for both immediately. Okay, so we have our Sommerfeld number already, 0.182, so it's going to be somewhere here. It's going to be at L over D of 1/2. Okay, so it's going to be somewhere around here, which is going to give us a value of around 5.1. And then we'll write that down on our worksheet later on, but we're going to keep it like this for now. And then here we have 0.182 at 1/2, which is somewhere here. And we see that we have around 0.81 for this one. So based on that, we can go back to our worksheet and we can say that Q over RCNL is equal to 5.1, and QS over Q is equal to 0.81. What this essentially means, QS over Q, is that 81% of your flow is going to go out through the sides, and 19% of your flow is going to go out through the bottom through gravity. Okay, so that's kind of how it's distributed. And it's fine to have a high side flow. It's completely fine to have a high side flow. It's not a problem. Okay, the only thing is that you do need to catch it back so that you can bring it back out. Okay, you can't just lose that flow all the time. If not, you would just have to feed new oil all the time, and it would be very expensive to feed new oil. Okay, so then we can solve for Q first. So Q is equal to 5.1 times R, C, and L. We have all those values. The one thing that you have to be careful is your N is going to be in, has to be in RPS. And then the other three can be in millimeters or it can be in meters. It doesn't matter, but usually we keep it in millimeters. So the other three could be millimeters. And if the other three are millimeters and you multiply them together, that means that Q is going to be equal to 219, in this case, millimeters cubed per second. Okay, if you leave the 3 units in millimeters, then you have millimeters cubed per second. If not, you would have meters cubed per second, but it would be a very small number. So it's better to use millimeters cubed. And then QS is going to be equal to 177, or 81% of 219, which is 177 meters cubed per second. Okay, and that concludes our problem. So we were able to find all these different variables based on this. Now, what we're going to do in the next video is we're going to do some more example problems, but we're going to introduce some more constraints to our problems and checking for stable lubrication as well as another criteria called Trumpless criteria. So we'll see you in the next videos for that.